Hello, thank you very much for coming to this focus session or watching the video online. My name is Viktor Ukleev from Polshare Institute, Switzerland. And first of all, I would like to thank the organizers of the APS March meeting and this focus session for giving me a chance to introduce you to the interplay between magnetic frustration, magnetocrystalline anisotropy, and Dzyaloshinskii-Moriya interactions in chiral cobalt zinc manganese alloys. And also I would like to thank my collaborators from PSI, RICONSEMS, ILL, EPFL, ALBA, SOLE, NIMS, and PNPI for helping me to realize this project, and it would be impossible to complete this work without them. And then let me introduce you into the chiral magnetism in exotic cobalt zinc manganese alloys that crystallize in the chiral cubic structure of a beta manganese type that belongs to the space group P4132 or P4332, depending on chirality, where cobalt ions, shown here as blue spheres, tend to occupy 8 C sites, while zinc and manganese ions, shown here as gray or pink spheres, respectively, tend to occupy 2 so-called hyperkagome, frustrated three-dimensional tritium lattice. The three-dimensional frustrated nature of this beta manganese type structure give us an opportunity to tune the magnetic properties of this family of alloys dramatically. For example, depending on manganese concentration, the magnetic ordering temperature transition from paramagnetic state to the ground, the heliomagnetic state, can be varied with manganese composition, and thus the TC can be pushed from around 180 K for 1010 compound down to 300 K in cobalt 8, zinc 8, manganese 4 compound, just by doping this crystal structure with manganese. At the same time, periodicity of the magnetic spiral, which is the result of the competition between symmetric exchange and antisymmetric Dzyaloshinskii-Moriya interaction, can be pushed from around 200 nanometer in 1010 compound down to around 100 nanometer in 776 compound, simultaneously with the decreasing of the ordering temperature from 480 K down to around 150 K. In this figure, I show you the phase diagram of magnetic structure depending on temperature and manganese concentration, where for lower manganese content or higher temperatures, the heliomagnetic state is dominant, while as we dope the system with manganese or decreasing with the temperature due to the frustrated three-dimensional lattice, the Q vector variation start to develop, change the periodicity of magnetic spiral is changes with temperature or with manganese composition. And by doping the system with more manganese ions, we can suppress the magnetic ordering at all and end up with the kind of spin glass state for the compositions of cobalt, zinc, and manganese 7 or above. The most famous compounds are 884, 893, 992, and 1010 due to their high ordering temperature and therefore the possibility to get the thermal equilibrium or metastable Skyrmion lattice at room temperature or even above. Also, it is interesting that in cobalt zinc manganese materials, the helical and also Skyrmion lattice periodicities can be changed with the varying temperature. And thus in 884, for example, that has the ordering temperature around room temperature, the helical and Skyrmion lattice periodicity just below TC is about 150 nanometers. But as you cool down to the cryogenic temperatures, to helium temperatures, 20 K or so, the heliomagnetic peak, the helical pitch gets as short as 70 nanometers. So there is a factor of 2 decrease in the periodicity of the magnetic spiral and Skyrmion lattice. Also, interestingly, this transition is accompanied with the lattice shape for magnetic skyrmions. Thus, from room temperature down to around 150 K, we have triangular or hexagonal skyrmion lattice that is typical for big 20 materials and other kind of cubic chiral magnets. But as we cool down, we get into the so-called amorphous skyrmion state, whereas the skyrmion lattice is orientationally disordered, and eventually we have deformed or square-like L-shaped skyrmion lattice at low temperatures. And this has been observed in both neutron scattering from bulk samples, but also resonant X-ray scattering and Lorentz transmission microscopy in the real space. But other interesting things happen as we go to the higher manganese compositions, where the manganese doping impacts the phase diagram dramatically. First of all, we have the A phase, which is just below TC, which is typical for other cobalt zinc manganese materials with the lower manganese content, and also typical to other cubic chiral compounds like copper selenide or B20 materials. So this A phase is attached directly to the paramagnetic phase, and skyrmion lattice pops up in the finite magnetic fields and in the narrow pocket just below the TC. But as we go down in temperature, we can stabilize another skyrmion phase at low temperatures that appears at higher magnetic fields and just above the spin glass transition temperature in this material. And this is unique to cobalt zinc manganese 776, but also a similar effect has been observed in copper selenide, with the difference that there's no spin glass phase at low temperature, and the effect of additional disordered skyrmion lattice phase is explained by the development of the strong cubic anisotropy at low temperatures in this multiferroic cubic chiral magnet. And again, this appearance of disordered skyrmion lattice phase has been observed both by bulk small angle neutron scattering and also by real space imaging with transmission electron microscopy. This is reported in this Science Advances paper from 2018. Next, we applied an arsenal of quantum beam probes that are available at the Paul Scherrer Institute here in Switzerland. Namely, we use neutron scattering, muon spectroscopy, and synchrotron soft X-ray scattering and spectroscopy to get the detailed information about the microscopic and macroscopic magnetic structures in this complicated cobalt zinc manganese alloy. Okay, and then let me explain the experimental tools that we used. First of all, the muon spin relaxation, the experiment that we have done at instrument GPS. It's a Swiss muon source at PSI. And we used the mu-SR in longitudinal geometry that allowed us to probe static and dynamic magnetic fluctuations in cobalt zinc manganese 776 single crystal in the time frame of a few microseconds. So this is slow magnetic fluctuations that are hardly accessible by any other probe, such as neutron scattering, inelastic neutron scattering, or inelastic X-ray scattering. In this technique, the muon beam is implanted into the sample with a penetration length of 100 or 200 micrometers, so it's actually bulk sensitive. Then muon decays inside the sample and emits the positron and two neutrinos. And the direction of the positron emission actually depends on the direction of the muon spin. So actually at time equals 0, where the muon beam is fully spin polarized and the muon couldn't sense any internal magnetic field inside the sample, the asymmetry of the positron emission is 100%. However, as the muon spin starts to precess in the internal field in our sample, the asymmetry of positron emission changes. And we can measure this asymmetry ratio as a function of time with a time resolution of around 100 nanoseconds. Here I show you the asymmetry functions measured from 0 to 2 microseconds for samples cobalt zinc manganese 776 and 884, measured at different temperatures at zero magnetic field. Immediately we can see that above ordering temperature, we have only very slow decay of the asymmetry function, just because we don't have any static magnetic ordering in the sample, and the paramagnetic fluctuations are too fast to be measured with muons. They're just outside of the MURSR sensitivity window. But as we cool down and go close to the TC, we have larger asymmetry change. So paramagnetic fluctuations are slowing down and enter the MURSR time window. And then once we reach the static magnetic ordering below 150K, we see very fast polarization decay that suggests some static helimagnetic ordering that immediately depolarize the muon beam. But once we go below the spin glass ordering temperature, we see that the asymmetry function firstly decays very fast and then has this very flat tail that is due to the so-called slow magnetic fluctuations. And similar picture is also observed for 884 material, but quantitatively the characteristic relaxation times for this higher ordering temperature crystal is quite different. I will show you this in the next slide. So here I show you both phase diagram for 776 and 884 materials. And the important reminder is that 776 has two different Skyrmion phases. One is just below TC and one is just above the spin glass transition temperature. Both of them appear in the finite magnetic field. But for 884 material, we only have the terminal equilibrium Skyrmion phase below the paramagnetic to helimagnetic transition. There's no second Skyrmion phase that can be manifested in this compound. And on the right side, I show you the graphs for the longitudinal relaxation rate measured by the MURSR spectroscopy at different fields. And in 776 material, we firstly see large enhancement of the paramagnetic fluctuations just below the TC that slow down as we cool the sample further. And another large peak at low temperatures between around 30K and 80K that corresponds to this low temperature Skyrmion lattice regime. While for 884 material, we see a large enhancement of the fluctuations just below the transition from paramagnetic to helimagnetic state. This is actually the region where the fast paramagnetic fluctuations slow down and enter the MURSR measurement window. Then the fluctuations slow down further, and there is another small peak for longitudinal fluctuations, again above the spin glass transition temperature, which is around 10 or 15K this material. But this peak is much less pronounced as in the 776 compound. Next, we use diffuse neutron scattering at D7 spectrometer at the ILO to probe the short-range spin correlations that appear in 776 cobalt zinc manganese powder sample. The polarization analysis in diffuse neutron scattering allows to discriminate between coherent and incoherent parts of the nuclear and magnetic scattering and extract weak signals from diffuse magnetic scattering that can be otherwise hidden by the nuclear background or magnetic background. What we have surprisingly observed is that the short-range correlations in 776, they persist from base temperature up to room temperature without sensing any static magnetic order in this material. So basically, this diffuse neutron scattering pattern exists both well above and well below the magnetic transition temperature, which is around 150 K. And the short-range correlations correspond roughly to the distances between manganese ion in the hyperpagoma site. Practically, the only difference that can be observed between low temperature, intermediate temperature, and high temperature diffraction patterns is that the magnetic scattering is enhanced due to the magnitude enhancement of magnetic moment at the base temperature. And it's terminally suppressed at around 300 K. And also we see additional magnetic Bragg peaks, additional magnetic contribution to the commensurate Bragg peaks that are basically the unresolved helical satellites sitting on the top of this, for example, 221, 310, 311 peaks that appear below the transition temperature. Otherwise, the diffuse magnetic scattering pattern is the same in the low temperature range. And the mean field model proposed by the Peter Derwet from PSI suggests that these short-range antiferromagnetic correlations are due to the nearest neighbor interaction between neighboring manganese ions situated at the 12D sites. And this model well corresponds to the experimentally observed diffuse neutron scattering pattern. So we don't need to go beyond the first neighbor interaction to reproduce the data we have at hand. However, it would be interesting to measure the single crystal diffuse neutron scattering data to see whether the higher order contributions, for example, J1, J5, that are shown to be quite important for the parent beta-manganese compounds, whether they can actually contribute to the short-range correlations, or using antiferromagnetic exchange between neighboring manganese ions is enough to explain the single crystal data or not. However, additional measurements on diffuse neutron scattering with single crystals would be required to reliably distinguish between these different theories. Next, we have also performed the soft X-ray spectroscopy experiments on 776 samples. We used polycrystalline ingots synthesized in the same way as single crystals, and studied them by sacrally polarized soft X-ray at extreme and various beam lines at S-Swiss light source and Alba synchrotrons respectively. And with the XMCD, we directly probe 3D to 2P transition to probe the magnetism with element selectivity at cobalt side and manganese side. And what we can see there in 776 material is that the XMCD signal from cobalt is quite large. It's about 10 or 20% of the total absorption, which is reasonable for metallic cobalt. But while for manganese, the XMCD signal is really, really tiny. What is interesting, the XMCD measured as a function of magnetic field cannot be saturated even by the high field of 6 Teslas. So that suggests some antiferromagnetic frustration in the manganese sublattice. We have also performed the transmission type soft X-ray scattering experiment on the same material. For this, we have prepared a thin lamella with a thickness of 200 nanometer of cobalt zinc manganese 776 and measured the small angle, resonant small angle X-ray scattering at both cobalt LH and manganese LH. And again, we have seen that the magnitude of the scattering signal at manganese side is much, much weaker than the one at cobalt side. From this, we can actually conclude that helium magnetism or main ferromagnetic moment is coming from cobalt only, while manganese has frustrated lattice and has the dominant antiferromagnetic coupling, and basically it doesn't participate pedimagnetic structure, but only contributes to these short-range correlations that we observed in the neutron scattering experiment. Another important notice, and I have already mentioned that previously the low temperature Skyrmion lattice was also observed in copper selenide single crystals, and it was explained by the development of the cubic anisotropy at low temperatures. And there is even theoretical proposals that the magnitude of the cubic anisotropy constant that is needed to stabilize the low temperature Skyrmion lattice by this simple formula. So what about the magnetic anisotropy in 776 single crystals? We have measured both squid magnetometry for 111, 100, and 110 main crystallographic directions. And basically in MH loops measured at both 146K just below the TC, or at low temperature at 50K, we don't see any difference for magnetization curves for these principal directions, already suggesting us that the magnetic anisotropy in this material is quite weak. It is very isotropic. Also, with the real space imaging performed with Lorentz microscopy, we can see that for low temperature phase for around 50K, we have very disordered magnetic structure that develops into more ordered but still worm-like magnetic domain, worm-like magnetic domain structure at higher temperatures as we worm. And finally, we end up with a well-ordered heliomagnetic state with a spiral propagation vector along the cubic axis. And we actually can see all three helical domains in one frame in this image at 140K. That means that the magnetic disorder is much stronger than magnetic anisotropy at low temperatures, also suggesting us that the magnetocrystalline anisotropy in this material at low temperatures is quite small compared to copper selenide case discussed in previous works. And the same is also suggested in the recent ESR data published in this paper by Eastern Cache Market Group. And in this report, they have measured magnetocrystalline anisotropies K1 and K2 for cobalt zinc manganese single crystals, 7 with different compositions, 776, 884, 992, and 1010. And they have shown that the really strong magnetic anisotropy may be observed in 992 materials, but or 1010, but in 776, the K1 constant is really low compared to these previous two materials with a lower manganese concentration. And we have calculated the threshold determined theoretically from the nature physics work for copper selenide that was discussed above. And actually, we have shown that the anisotropy constant is well below the theoretically proposed limit for the low temperature Skyrmion phase. Therefore, we need an additional mechanism that stabilizes Skyrmions at low temperature. The magnetocrystalline anisotropy is not the one that can explain the occurrence of the additional Skyrmion phase in cobalt zinc manganese 776. Therefore, the fluctuation scenario that we have discussed before, the additional fluctuations that we observed at low temperatures just above the spin glass transition temperature in the temperature window that corresponds well to the low temperature Skyrmion lattice phase in 776, and also occurrence of the short range magnetic correlations due to the frustrated lattice of manganese ions, and also the idea that manganese ions are 12D sites are all frustrated, while the helomagnetic state and Skyrmion state is mainly maintained by cobalt located at 8C sites. All this, and also the fact that magnetic anisotropy is very small in some sense, these all facts suggest that this disordered or low temperature Skyrmion state in cobalt zinc manganese has different origin than the low temperature state that has been observed in copper selenide ferromagnet. Another topic I would like to discuss is magnetic interaction in another cobalt zinc manganese alloy with the lower manganese concentration in cobalt 8 zinc 8 manganese 4. And the question is, what's driving the Q vector increase at low temperatures that I have also mentioned a few slides ago. Again, here we can create a metastable Skyrmion lattice by the fuel cooling, and it goes from triangular Skyrmion lattice arrangement into the orientationally disordered lattice at intermediate temperatures, and at low temperatures it changes the Skyrmion shape and forms the L-shaped or Tetris-like structure at low temperatures, a supercooled state. And again, in this work done with ESR, we have seen that the cubic anisotropy constant for 884 material, here it's in red, it also increases at low temperatures. So maybe the occurrence of this cubic anisotropy and its development over low temperatures promotes the helical pitch change by a factor of 2 from 300 to 20K in 884. And maybe it also can drive the triangular to this square-like 44 Skyrmion lattice transition for metastable supercooled Skyrmion lattice state. Let's see. In previous works, we have shown that in micromagnetic simulation, one can tune the relative ratio between the exchange interaction and the Dzyaloshinskii-Moriya interaction to reproduce this behavior with the Skyrmion deformation and the spiral pitch change, just by decreasing the exchange stiffness in this material or exchange interaction in this material in a magnetic field in the presence of the cubic anisotropy. And this deformation from triangle lattice into the orientationally disordered lattice and finally into a deformed Skyrmion lattice state could be reproduced by micromagnetic simulations. And also, yeah, again, this is the experimental image obtained with the X-ray imaging. And we had a surprisingly good reproduction of this experimental results obtained with the soft X-ray scattering and micromagnetic simulations, where we just linearly vary the exchange stiffness in cobalt zinc manganese 884 material and compared it with the temperature dependence of the Q vector of the Skyrmion lattice. But in fact, in this simulation, we couldn't really distinguish between the influences of the exchange interaction change and the Dzyaloshinskii-Moriya change, because we could, here we could either change exchange stiffness linearly or the Dzyaloshinskii-Moriya parameter and obtain the same results, because they equally contribute into the spiral or Skyrmion lattice parameter. And recently, a neutron scattering group led by Grigoriev, they introduced a new technique called spin wave sums to probe the spin waves in cubic chiral magnets based on the small angle scattering of polarized or non-polarized neutrons from chiral single crystals with the DMI and exchange interaction, and basically in the field polarized state. And inelastic neutron scattering from spin waves in this material in the fully polarized state has asymmetric shape depending on the chirality of the magnetic spiral and the initial polarization of neutrons. And it can be clearly seen that the non-reciprocal propagation of the spin waves in cubic chiral magnets can be very effectively probed with this polarized neutron scattering technique. And the advantage of this technique is that it has a much better k-space resolution than classical inelastic neutron scattering. And it doesn't require large sample volumes, though of course you can only measure materials with relatively low exchange stiffness. And the only parameter you can measure in this way by measuring the field dependence of this spin wave sans patterns is the exchange stiffness. You cannot deduce higher order exchange interactions. Still, this technique has been applied to multiple B20 materials and copper selenide, and exchange stiffness was measured very nicely for all of them. And basically all these cubic chiral materials with B20 structure and copper selenide, they show the same behavior of the spin wave stiffness, namely its increases from TC towards low temperatures. And we used the same technique to probe the exchange stiffness in cobalt zinc manganese 884. And we could again observe this asymmetric distribution of spin wave sans intensity, suggesting that we really have the non-reciprocal propagation of the heliomagnetic magnons in this material, which is not surprising because it has the chiral magnetic structure and also DMI. And we have measured the temperature dependence of this spin wave scattering pattern. And interestingly, we can see a very clear spin wave scattering signal. Now I show you the results that we have obtained with non-polarized neutrons. So there's no difference between left and right, but we can still extract the spin wave information without losing anything. And we can clearly see the spin wave scattering at 250K here, for example, around 150K. But as we cool down more, the spin wave intensity, spin wave sans intensity gets much weaker, and the distribution gets much broader. So it's getting quite difficult to distinguish between the cutoff of this spin wave scattering intensity and between the width of this scattering peak, from which we actually deduce the the spin wave stiffness eventually. However, we could reliably obtain the exchange and parameter from this data. Here it's shown in blue, and we again see the increase of the exchange parameter from room temperature towards low temperatures. However, analysis of the lower temperature data is very complicated or even impossible because of the large damping and very low signal at lower temperatures. And also from this dependence, we can calculate the Dzyaloshinskii-Moriya parameter using the famous formula from Bach-Jensen model, just having the exchange stiffness and the spiral Q vector. We can calculate the Dzyaloshinskii-Moriya parameter, and it's shown here. And interestingly, we see that in order to satisfy this formula and describe the spiral pitch change on cooling, we also have to introduce the temperature change of the Dzyaloshinskii-Moriya interaction. Also, as I already said, we have a very large increase of the spin wave damping below. So here the spin waves are damped just because of the fluctuations near the paramagnetic transition. But very surprisingly, the spin wave damping is also increases dramatically as we pass around 150K. And again, we related to the frustration of manganese moments at 12D side and the short range correlations that also exist in this 884 material. However, one can also think of alternative mechanisms that may explain the Q vector change as a function of temperature. Maybe in addition to the thermal variation of exchange and the Dzyaloshinskii-Moriya interaction, one can also think of the so-called anisotropic exchange interaction that is a higher order term in this formula, but it also can affect the periodicity of magnetic spiral. And that would be a subject of our next studies using X-ray and neutron scatterings. Just to conclude, we used multiple quantum beam probes, namely muons, neutrons, and soft X-rays, to provide a complementary picture of the long-range magnetic ordering and short-range correlations in Skyrmion hosting cobalt zinc manganese alloys. We have observed two peaks in slow magnetic relaxation rates just below TC and just above spin glass transition in this material. And we connect the low temperature peak with the stability of the low temperature disordered Skyrmion phase. Also, we have successfully observed short-range antiferromagnetic correlations that persist from lowest temperatures to 300K in cobalt zinc manganese alloys. And also, we identified that the long-range magnetic ordering is mainly maintained by cobalt ions at 8C side, while manganese at 12D side mainly frustrated and do not participate in helimagnetic ordering, but rather in short-range correlations. Also, we have proved that the low temperature disordered Skyrmion phase in cobalt zinc manganese 706 is stabilized by slow magnetic fluctuations rather than by magnetic anisotropy, similarly, which is the main mechanism for disordered Skyrmion at low temperature in copper to selenium 3. And also for cobalt zinc manganese 884, we have shown that the exchange interaction DMI, magnetocrystalline anisotropy, and potentially anisotropic exchange vary with the temperature. And this is probably the case in other materials in this cobalt zinc manganese family, which makes the story even more complicated. Please take a look at these two papers to get further details. Finally, I would like to acknowledge large-scale neutron and X-ray facilities where we have performed our experiments, and funding agencies SNF, JST, JSPS, and Horizon 2020. And thank you very much for your attention.